again. So we're on to lecture 6 on series, more geometric series. What I wanted to talk about today was geometric series and rational numbers, well, more generally, real numbers. The decimal expansion, infinite, the decimal expansion to the right of the decimal point can really be thought of as a series in a very natural way. And rational numbers can really be thought of as geometric series in a very, very natural way. So let's just review what a natural number is and what they look like. So, a rational number. Rational, think ratio when you think rational number. Ratio. What are ratios? Well, ratios are, quotients. Rational numbers are exactly those real numbers that can be written as fractions. And when I say fractions, I don't mean 1.6 over pi. I mean ratios of integers, like 1/2 or 5/9 or -8/3 and things like that. Okay, ratios of integers. And integers, of course, are whole numbers and they're negatives. Now, it's a fact. If you try to take a rational number like this and you do long division and divide 9 into 5, for instance, you'll eventually reach a point where you just repeat over and over again. It's a fact that rational numbers are precisely those numbers that either have finite decimal expansions or eventually repeating decimal expansions. Like finite decimal expansion, you might have, let's do this, you might have like 3.2569, and then it just stops there. How do you write that as a fraction? Well, that is 32569 over 10000, 4 zeros. But you might also get something like what we have down here. And the question is how to write that as a fraction. Okay, this is equal to a over b for some integers a and b, but how do you write that? So let's take a moment and just think about what these decimal expansions mean. You might remember this so long ago in grade school, the tens place. So this 3 is in the 10 to the 0th place. It's called the ones place. We think of that as 3 times 10 to the 0. This 2 is in the -1 place. We think of that as 2 times 10 to the -1. Right? 10 to the -1 is 1/10. So let me just make sure this makes sense. This is 2 times 1/10, which of course is 0.2, right? That's this. And then we've got, this is the 10 to the -2 place. So this is 5 times 10 to the -2, which is 5 times 1/100th, which again is 0.05, right? Edit, undo, which again is 5 times 1/100th, which equals 0.05. And we've got a couple more. This is plus 6 times 10 to the -3rd plus 9 times 10 to the -4th. And let's just make sure that makes sense. Okay, so 3 times 10 to the 0 is just 3, plus 2/10 plus 5/100th plus 6 1,000ths plus 9 1/10,000ths. And if I find a common denominator, it's going to be 10,000, right? So that's going to be 30,000 plus 2,000, right? Because I need to multiply this by 100. Sorry. Let's go back. It's going to be, yeah, 1,000, 10,000. So I'm going to get 3 times 10,000, which is 30,000, plus 2 times 1,000, which is 2,000, plus 5 times, what do I multiply by 100 to get 10,000? I multiply by 100, 500, plus 6 times 10, 60, plus 9 over 10,000, which of course is equal to 32569 over 10,000. Right? Exactly what I had up here. Exactly what I had said it was. And of course, there's a formula for that. You just look at the number of places you go to the right of the decimal point. That's the number of zeros in the denominator. And it comes down to every fraction whose denominator has factors that are either powers of 2 or powers of 3 or multiples of powers of 2 and powers of 3. I mean, sorry. Powers of 2 and powers of 5 are multiple of 2's and 5's, because 10 is divisible by 2 and 5, can be rewritten as a finite decimal expansion. But now we've got these infinite decimal expansions. Let me take a moment to just erase what we did and think about how to deal with the infinite ones. Okay, so according to what we've said before, this should be some sort of series, right? This should be powers of 10 we're working with. It should equal 2 times 10 to the 0 plus 1 times 10 to the minus 1 plus 8 times 10 to the minus 2 plus 5 times 10 to the minus 3 plus 3 times 10 to the minus 4 plus 5 times 10 to the minus 5 plus 3 times 10 to the minus 6, and so on down the road, right? Just repeat over and over again. Well, let's suppose that's what we want and see what we can actually get, because that is exactly what we mean when we do this. It is an infinite series. So the first thing we want to notice is these first terms. I want to kind of get rid of these first terms. 2.18, what is that equal to? Well, we just mentioned that's equal to 218 over 10 squared. And you can check, that's 200 plus 10 plus 8 over 10 squared when you add common denominators. Now, for these other ones, I'm going to actually combine the 5's and the 3's here. And we're going to get plus, well, what's 5 10 over 10 cubed plus 3 over 10 to the 4th? That's going to be 53 over 10 to the 4th, right? What's 5 times 10 to the minus 5 plus 3 times 10 to the minus 6? That's going to be 53 over 10 to the minus 6. And the next pair is going to be 53 over, sorry, when in the denominator, it's going to be just 10 to the 6th, 10 to the 8th. I'm just going to get even powers of 10, right? So I can write that as a geometric series. So this is going to be 218 over 100 plus, how is that written as a series? Well, it's not quite what I want because I'm not going up by consecutive powers of 10. So let's rewrite that again. It's even powers of 10, right? I'm going to write that as 100. 10 to the 4th is 100 squared. Right? 10 to the 6th is 100 cubed, right? 6 is 2 times 3, so that's 100 cubed. 10 to the 8th is 100 squared. I mean to the 4th, 100 to the 4th, because 8 is 2 times 4, 10 squared is 100. So we can rewrite this as 218 over 100 plus, now we can write this as a series. This is the sum, I equal 2 to infinity of 53 over 100 to the I, which is, well, we came up with a formula for that where we got this 218 over 100 plus, that's going to be, what's my M here? Let's just write out, what's my R? R is 1/100th. A is 53, right? And M is 2. So this is going to be 53 times 1/100th squared, R squared, over 1 minus 1/100th. Okay, and this can be simplified. This can be simplified to 218 over 100. So I'm going to bring the 100 squared down and make that 1 over 100 squared, that, and bring 1/100 squared through. So it's going to be plus 53. The 100 is left, and when I bring the other 100 through, I get 100 minus 1, which is 99, which can be rewritten as 218 times 99 plus 53 over 100 times 99. Okay, so so we just found a way to write this as a fraction. Of course, you need a calculator. Get 218 times 99 plus 53. That's the numerator, and 9,900 is going to be the denominator. Okay, I'm going to kind of give you a shortcut for this because it's, you may as well see a shortcut. And this is probably the way it was taught in junior high school or elementary school whenever it was taught, because it's a little bit easier to see. And it works just as well. So let me get this down to size and give you a shortcut. Okay, so how are we going to see a shortcut? We've already got x is defined as 2.185353, and so on down the road, right? I'm going to multiply it by consecutive powers, by powers of 10 that allow me to line up the decimal expansion. First, I want to get rid of the 2.18. And so it's just 0.53, 0.53 down after the decimal expansion. So if I say this is 100x, that's going to be 218.53, etc., which of course, as we saw, was 218 plus 53 times the sum, I equals 0, I equals 2 to infinity of 1 over 10 to the I, which we figured, no, in this case 0, I equals 0, I equals 1. We're starting there. I equals 1 to infinity of 1 over 100 to the I, which we saw converges. And I'm just mentioning that just to kind of point out things are going to work out right. But now I want to multiply by the next power of 10 that allows me to line up the 5 3s. So that's going to be 10,000, right? Because if I have 10,000, it's going to move it over again. So 10,000 x is equal to 21853.5353, etc. And you notice this decimal expansion, this part after the decimal place, is exactly that which converges. So how am I going to work this? Well, I'm going to have 10,000x, which equals 21853.5353, etc., minus 100x, which equals 218.5353, etc. If I subtract those two things, well, on the one hand, I get 10,000 minus 100, which is 9,900, right, x. On the other hand, when I subtract the right-hand side, these decimals cancel. And you know the decimal cancels from your experience with arithmetic, but more precisely now we know they cancel because they're both just these sums 53 times these infinite series that converge, and so we can combine them and actually get the series of 0. They cancel because they're infinite series, and they completely, and everything still converges to what they should be. So now when I do the subtraction, 3 minus 8 is 5, 4 minus 1 is 3, 6, I get this, and I get x is equal to 21,635 over 9900, oops, 00. And you should check that this ends up being the same thing. Okay, and that's good for right now. Bye-bye.